Okay, good afternoon everybody. Welcome to my presentation on how to optimise the performance of single atom catalysts on lithium sulfur batteries through machine learning. So in this presentation I'll detail the aims of my thesis, some background on the key concepts including machine learning, candidate selection methods, transfer learning, and the results I was able to obtain through these, as well as the main conclusions drawn from this thesis. So the main aim was to design a procedure to evaluate the performance of different single atom catalysts. So this included producing a machine learning model that has excellent performance on unseen data, propose effective candidate selection methods to limit the number of structural relaxation calculations, which are how we obtain the effectiveness of the single atom catalyst. And these calculations are very computationally expensive and sometimes take days to run per structure. So the whole aim of the game is to reduce the amount of these calculations required. I also investigated transfer learning as a means of speeding up the training process for new machine learning models. So the overview of the proposed workflow is that we use transfer learning to speed up the machine learning process. Then we use that machine learning model to predict binding energy between the lithium polysulfide molecules and the single atom catalyst, so we can see how strongly the interaction is between them. Then we use these predictions in conjunction with a candidate selection method to find the most promising candidates for structural relaxation, and finally we relax those structures to find how well the single atom catalyst is performing. So the problem that the world faces today is that technology is advancing at a very rapid rate and the demand for high capacity batteries is at an all-time high. So all of our phones, all our laptops, and with the recent electric vehicle boom, these all rely upon lithium-ion batteries currently. But lithium is a very finite resource, and at the moment less than 5% of lithium-ion batteries are currently recycled. So it's very important to maximise the amount of productivity we can obtain from the lithium that we mine from the ground. So the lithium sulfur battery could be the perfect candidate to replace lithium-ion batteries. So this was first discovered in the 1960s, and fortunately the sulfur, which is used to create the cathode in the battery, is very cheap and eco-friendly. These have a very high theoretical energy density, eclipsing that of lithium-ion batteries. So you can see on the graphic here on the right, it is over 6 times, it has over the 6 times the theoretical capacity of lithium-ion batteries. Additionally, lithium-ion batteries are already relatively close to their theoretical maximum since they've been around for quite a while. Unfortunately, lithium-ion battery development has been stagnated a little bit because of issues, particularly with the stability of the battery over many cycles. So there are 2 main issues with lithium sulfur batteries. The first is dendritic formation of lithium onto the anode during stripping and plating as the battery is discharged and charged. So this happens because certain sites are more favourable for this lithium deposition. And this is like the unfortunate snow conditions in Australia. You'll get snow falling and some may fall under trees where it's nice and shady and you'll get drifts, and some may fall on rocks and road where it melts. And as you get more snow falling and then it melts during the day and solidifies during the night, you'll get larger and larger drifts and thinner patches. This is what occurs inside these lithium sulfur batteries. And if these dendrites become so large, they may reach the cathode and short circuit the cell, which destroys the battery instantly. Alternatively, they can also snap off and form this dead lithium in the centre. Now this dead lithium is no longer connected to the anode electrically, so it's completely useless to the battery and we lose active material and it's just floating around doing nothing. The second issue is shuttling of the lithium polysulfide intermediates that are produced during the battery process. So these longer chain lithium polysulfides are soluble in the electrolyte. So that means that they can dissolve and migrate between the electrodes if the concentration density gets too large. But these are meant to be reduced to the shorter chain lithium polysulfide molecules, I'll call them LIPs from now on, which are insoluble and then they form back onto the electrodes. So again, if they shuttle and then they reduce in the wrong place, they can form insulating deposits on the electrodes, which covers them, and then charge cannot flow through the battery. So again, it struggles. But recently, single atom catalysts have emerged as a potential solution to this problem. So single atom catalysts usually consist of a transition metal, that's that red atom in the middle, supported on a carbon structure. So for this thesis, I investigated a nitrogen-doped graphene substrate. So these blue ones are nitrogen and the grey ones are the carbons. So these are a dual-acting solution that, as you probably know, catalysts encourage reactions by lowering the activation energy. So by encouraging the LIPS molecules to reduce, we can get them into an insoluble form before they have a chance to migrate between electrodes. These single atom catalysts also provide uniform active sites to encourage even lithium deposition, so we are also removing the dendrites. So the main indicator of the performance of single atom catalysts is how strong the absorption energy is between the single atom catalyst and these LIPS molecules that are formed. So density functional theory calculations are required to find this minimum binding absorption energy. And so these involve taking the crystal structure you put in, and it moves the atoms around until the forces between these atoms reduce down to near zero. So this is important because systems tend towards their lowest energy state. So we want to find this lowest energy state, and we want to find the absorption energy, which is the strength of the interaction between the LIPS molecule and the catalyst. This is an indicator of how effective the catalyst is at reducing these lithium polysulfide molecules. So as I mentioned earlier, these structural relaxations, the ones I was performing, took about 30 to 50 hours each to perform. And if you have 50,000 configurations you want to look at, it's not really a suitable method of doing this. But recently, machine learning has been employed to speed up this process. So machine learning is a subset of artificial intelligence and is a method of modelling complicated relationships between variables. This can be used for many different applications, including classification and regression, and many different models exist, such as kernel ridge regressors and neural networks, each of which are suited to different applications. So, machine learning and single atom catalysts. Most current literature use data sets consisting of the crystal structures with a binding energy associated with them. So this is generated with a single point DFT calculation. So it's relatively quick to perform because it only takes a snapshot of the cell and finds the energy between the single atom catalyst and the LIPS molecule, instead of going through the whole iterative relaxation state. So these are relatively quick data sets to produce. But unfortunately, traditional machine learning models are not able to take the crystal directly as an input. They need to have the crystal changed somehow into a fixed length feature vector, which just consists of numbers. So by doing this, we lose some information about the actual crystal itself. Then using the predictions for the binding energies, we use some sort of candidate selection method, and then we relax those molecules to find the minimum absorption energy. Fortunately, crystal graph convolutional neural networks have been recently developed to predict material properties. These can actually take the raw crystals as the input with no changes to them, so we don't lose any information there. So these are perfect for predicting the binding energy between the single atom catalyst and substrate and the lithium polysulfide intermediates. So the CGCNN I adapted was trained on two data sets, one for a zinc catalyst and one for an iron catalyst. The hyperparameters were tuned using grid search, which is an efficient method of refining it so that it performs as well as it can for this problem. And I used 300 epochs, which is each pass of the training data through the network. A typical validation loss versus epoch curve can be seen on the right, where initially the performance is quite poor, but then it rapidly stabilizes and converges to a good solution. So the performance of each of the CGCNN on each of these data sets was excellent. It's actually quite hard to see, but the green line there is the ideal predictions line, and the red line is the line of best fit. So this model was able to achieve excellent solutions for both the iron data set and the zinc data set. So these were able to obtain R-squared values of 0.99 and above, and mean absolute errors of about 0.1 electron volts. These data sets, the model performed particularly well on unseen data compared to the traditional methods. An excellent example of this, in red, is the traditional method for predicting the zinc data set binding energies. So on the training set, it performed extremely well. However, when we get to the unseen test data set, the performance suffers quite significantly. Whereas for the CGCNN, it performed similarly very good on the training set, but then the performance did not suffer quite as much on the test set. So this is really good because this is the best indicator of how well the model generalizes or performs on unseen data, is the performance on this test set. So this is likely the case because the original model, or the traditional model, was likely remembering the data somewhat, or overfitting as it's called in machine learning. Whereas, so if you provide new data, it's not able to predict it as well because it only remembers what it's being taught, rather than observing the relationship. So using these predictions, we can use a couple of methods to identify the most suitable structures for relaxation. So the absorption energy space is quite hilly, and so there are many local minima which can cause convergence to get stuck. So the first method I investigated was lowest value selection. So we select the lowest energy binding energies, and so we effectively cap the value of the absorption energy. So this can be shown as the cap here. And these structures will relax to their nearest local minimum. The second investigated was farthest point sampling, which spreads out the starting points so that we relax to a different local minimum each time. However, some of these local minima may be poor, like this one above, but some may be excellent, like this one here. These were the results I obtained. In green is data from a similar paper from published literature. In blue is the lowest value selection, and in orange is the farthest point selection. So my data set my predictions were not quite as low or strong as the published literature, but they were pretty good considering the computational restraints I had, I could only relax 5 molecules for each of the LIPS molecule data sets, whereas existing literature was relaxing 10 plus. So this is a comparison with multiple other papers. My results are in the black line, and the other ones are the coloured bars. So this is for Li2S1, S2, S4, S6, and S8. As you can see, I'm right in the mix despite these computational restraints that I had, and it'd be expected that these would only improve with more computational power available. So transfer learning is the reuse of a model for a similar problem. So this means that we can cut out the amount of training passes or epochs required significantly, as it turns out. So the models trained on the iron and zinc data sets respectively were used on each other. And then limited epoch retraining was conducted to see if fast results could be made. So the iron model was subjected to 10 epochs of retraining with the zinc data, and as you can see, the results were excellent. They were comparable to that of 300 epochs of retraining from scratch. For comparison, this is 10 epochs of training from scratch with just the zinc data. No meaningful trend is observed. Interestingly though, the zinc model, when subjected to 20 epochs of retraining with the iron data, was not able to extract a meaningful trend. You can see that the ideal predictions line is very different to the line of best fit. And again, from scratch, it performed pretty well. The two lines are pretty close, and the spreads they're okay. So this is likely because, as you can see, there are about 6 times fewer data points in the zinc set, and they are less structurally diverse because there's less outliers. So it's not able to account for the larger data set, which is more noisy. So the main conclusion is that an efficient procedure has been developed to evaluate the performance of single atom catalysts. Now this can be expanded to different transition metal catalysts and allow them to be evaluated rapidly at a low cost. The CGCNN is well suited to this application, exhibiting excellent performance, particularly on unseen data. The candidate selection methods showed promise, but more investigation is required to more molecules per LIPS molecule. And transfer learning has great potential, but again, this would be excellent to see performance on other transition metal single atom catalysts. Some other recommendations for future research is to train a model on the already relaxed LIPS molecules. However, as I mentioned earlier, this would be very computationally expensive, so you probably need a big data center or outsource a lot of it to different servers. This could also be extended to sodium sulfur batteries and similar. Thank you very much for listening. Do you have any questions?
So, what hardware do you use? How long did you take for 300 depart?
So I used my home PC, which has 16 gigs of RAM, and it took about 26 hours to train for the iron dataset, and about half that for the zinc dataset.
So I suppose you use GPU, right?
Actually, no. No, sorry, yes, I did. I used PyTorch, which is GPU compatible.
Yeah. Do you remember the model name?
No, I don't. I remember we looked at purchasing 4090 through the Thesis, but through the scholarship funds, but I think it was a bit too hard because we were only meant to use the scholarship funds to gain access to other other not physical things, either lab access or online servers to help you. So that kind of stagnated.
Yes, actually, because I only do some research stuff at the lab. This work is more about the machine learning, the computer calculations. So the fund is for the bench phase. So we do buy some subscription online.
Yeah, so we spent about $600 to purchase CPU time on a server to perform these structural relaxations. And that $600 only went as far as about 30 structural relaxations, taking up over 1,000 hours of CPU time. So that is a good statistic for how intense these calculations are and why it's important to employ a machine learning model and good candidate selections methods so that you minimize the amount of those structural relaxations needed.
You talk about a good selection method. Can you go back to the candidate selection results slide? Why didn't you choose to use the generalized convex hull method if that produced better results in other literature?
So the generalized convex hull was used in one paper that I studied a lot from 2021, and it produced very good results, but it's a bit of a tricky one because it's been taken somewhat out of context. So the generalized convex hull is originally developed to predict stable phases in thermodynamic systems. So you'll plot on the x-axis the thermodynamic variable, which is usually temperature, and then on the y-axis you have the energy of the molecule. And at the vertices along the bottom of the generalized convex hull are where the stable phases occur, like ice in water or water at room temperature. But if you have too high an energy at a temperature, you will migrate to one of these bottom edge vertices. So they used the GCH to identify stable structures. So it's been taken somewhat out of context, but the idea sort of makes sense, that the stable structures are the ones that are closest to relaxation and that are the closest to how they will actually interact if it were put to a laboratory test. So I actually got in contact with the author of this paper, and he recommended to investigate lowest value selection and farthest point sampling as an alternative to GCH, which relies upon many assumptions and hasn't been proven to work yet, although the results are pretty good. And so the GCH results are these red bars here, and then the other ones are from other papers using different methods.
Thanks, Ali.
Thank you very much.